Hello students, welcome to lecture number 5. Today's topic is MIPS instruction, some examples and demonstrations. So what we're going to do today is that we will take it forward from what we have left in the last lecture, and we'll do more advanced level examples to see how whatever you learned till now in terms of MIPS instruction can be applied further for more advanced level instructions. Okay, so let's get started. Okay, so let's first have a look at something called registers versus memory. So what is a spilling register? So when there are more variables than register, then compiler tries to keep most frequently used variables in the memory, right? So what I mean by that is basically in a program you are basically having more variables than the total number of registers that a MIPS 32-bit can afford, right? So then what the compiler will try to do is that it will try to keep the most frequent ones only in the registers, and the remaining ones it will spill into somewhere. Okay, we'll see where. So why not just keep all variables in memory? Obvious answer is that the process of keeping everything in memory will result into more access time, and smaller is faster, therefore registers are faster than memory. So MIPS arithmetic instructions can read 2 registers, operate on them, and write 1 register per instruction, right? And MIPS data transfer only reads or write 1 operand per instruction, and no operation is possible, right? So some basics. So therefore the concept of spilling register tells you is that you only keep the most frequently used ones in the registers, rest you have to spill it to some external place. So let's do one example. Let's say you have a piece of code given as A8 equals to H plus A8. So the corresponding MIPS code will be as follows: LW $T0, 32 $S3. So as you could see, A8 stands for 32 $S3. The reason is H is associated with register S2, right? And the base address of AI is in register number S3. So here S3 is actually having the base address for the array AI. So therefore what we have done is we have added the content of the base address with the content of 32 to get the effective address, right? And from there it will be loaded onto $T0. So once the word is loaded onto the register $T0, then it is added with the value of $S2, because $S2 is actually associated with the variable H. And once that is done, then typically it is again stored back into $T0. And this $T0 has to be again now stored back onto the memory. So we are again using SW word. So it's a combination of LW and SW. As you could see, we load from memory onto the register, and then again at the end we will store it back onto the memory from the register. So therefore we have $T0, 32, $S3. Why we are using the same $S3 is because we want to store it back to the same memory location, same array AI, right? So that's how we have 3 instructions in the MIPS code corresponding to 1 piece of line of code for a high level language, which you see here. Okay, so let's do one more example. Imagine you have a high level code. It is a swapping example. So you have this high level code on the left side. Temp equals to VK, VK equals to VK plus 1, VK plus 1 equals to temp. So the corresponding MIPS code of it will be as follows. You will first, what you will try to do, you will try to get the address. Okay, so what we'll do is that we are actually trying to add $A1 with itself in order to create an effect of 2 into K. Let's say K is associated with $A1. Okay. Now 2 into K is stored into $T1, then again $T1 is again added with itself. This will create an effect of 4 into k, because we are adding 2k plus 2k, and again it is stored back into $t1. So therefore we have add $t1 comma $t1 comma $t1. So now since we have got this 4 into k thing done, right, why we are getting this 4 into k thing done is because due to MIPS alignment restriction, we assume that every piece of index in a memory array is 4 byte. So therefore we will have to multiply that with 4, as I spoke about it in the last lecture. So once this 4 into k thing is done, which is stored into $t1, it is added with $a0, because $a0 is having the content, right, and from there we again put it back into $t1, right. So once we have this $t1 done, then from there we will actually load the word into $t0, isn't it? So let me repeat what I'm saying. We have done till $t1, and then the base of the array is stored in, for example, $a0, so that the base address is again added with the offset, which is stored into $t1, and then again it is stored back into $t1, the newly computed value. This newly computed value, which is $t1, from there with an offset of 0 we are loading the word into $t0, right, because now we don't need to add any offset, it's already there in the very first location of the memory array, right. So from $t1 with an offset of 0 we are loading the word directly into $t0. Once we have this $t0 loaded, then the next step would be to load the next content, which is again after 4 bytes. So therefore in the next content of it will be LW $t2 comma 4 $t1, right. So we are actually loading vk plus 1, because k plus 1 is the next index, which is after 4 bytes. So because every index is occupying a space of 4 bytes, so therefore with an index of 4 comma 4 in brackets $t1, from there we will load the word into $t2, right, and again from $t2, once it is loaded there, now what we'll do the swapping. We'll just swap the locations. SW $t2 goes to 0th location of $t1, and SW $t0 goes to 4 $t1, right. So as you could see, the location of $t0 $t2 has been swapped. Previously $t0 was in 0 $t1, now it is in 4 $t1, and $t2, which was previously in 4 $t1, is now in 0 $t1. And once this swapping process is done, then what we'll do, we'll jump back to the register which is $RA, which is having the return address, okay, from where we have actually come. We'll again jump back to the same place, right. So as you could see here, again a summary of what I just said in the swapping example is, we are basically just trying to first compute the actual value by multiplying it with 4. This multiplication of 4 with the index k in order to get the actual value of the offset, that has to be gotten by adding a0 with itself, and again once we have stored the result into t1, again t1 is added with itself, so that now we have 4 into k. That's the first step. The next step would be now to add the base address, okay, of the array, same as in it is stored in $a0. So therefore we have a0 plus 4k. Now we have got the effective location in the memory. From there we will again load the value of the word into $t1. Once it is there, once we have the updated value in t1, then we can load the word into a new location t2, t0, and again we can do the next location, which is vk plus 1. We can store it into t2 from 4 $t1, and then ultimately we will swap it, right. So that's how things are done here. So we will first compute the effective address, then we'll load it, then we'll store it, and finally we'll jump back to the original program from where we have made the jump. Okay, so we jump back to the register whose location is stored in $RA. Okay, let's move to the next example. Now let me give you some idea about MIPS branching. Now MIPS processor, as I said, has conditional instructions. So branch or not equal, BNE is one of the very famous ones. Then we have a next one which is called branch on equal, which is BEQ. And these are all part of I-type instructions. Okay, these are not part of J-type instructions because these are conditional control flow instructions. So that means we'll do a type of jumping, but it's not unconditional, it's conditional. So that's why we call it part of I-type instructions. So let's say BNE $T0, $T1, label is one of the examples of how it can be written. Second is BQ $T0, $T1, label. So let's say let's do an example. Let's say if I equal to j, then h equals to I plus j. So what I'm saying here basically is, if we try to associate the variables I and j with $S0 and $S1 registers, then if we can write the first step to check it as BNE $S0, $S1. That is, if branching will happen if the content of these two are not equal, then it will jump to a particular location which is given by label. So it will jump to label. If they are not equal, if they are equal, then we will add the value of $S0 and $S1, and then we will store it to $S3. So here $S3 is associated with h, $S0 is associated with I, and $S1 is associated with j. Right? So as you see here, we have used three statements: BNE, add, and then label. Right? So this is one of the examples of how we can do MIPS branching. So this is called branching. We have branched to label if the conditions of $S0 and $S1 don't match. That means the condition means the contents of both the registers are not equal. Then only we will do the label jumping. Okay. So this so-called jumping is technically called branching, because we are branching to a particular location in the program which is given by label. Okay, let's do one more example. So in this, the piece of C code is, if I is not equal to j, then h equals to I plus j, else h equals to I minus j. So what I'm trying to do here is, let's say we have associated $S4 with I, $S5 with j, $S3 with h. So these are all compiler associations done. I'm just taking it as an example here. So if BQ $S4, $S5, label 1. So if I and j are equal, okay, that means I'm first testing the else condition, because if it is not equal, it will anyways do the addition, right? But if it is equal, then I'm checking and I'm testing that condition. So using the statement BQ. In BQ, if the content of $S4 and $S5 are equal, then it will jump to label number 1. In label number 1, what do we have? We have sub $S3, $S4, $S5. That means we are subtracting $S4 and $S5 between themselves, and then we are storing the value at $S3. So here S3 is associated with h, $S4 is associated with I, and $S5 is associated with j. Right? So this happens when the condition is equal. What if it is not equal? If it is not equal, then automatically that label, that branching to label 1 will not happen, and rather it will proceed to the next MIPS statement, okay, which is the next line, which is given by add. $S3 is the output where we store the value of h, and $S4 and $S5 are added with itself. Okay, that means they are added between themselves. So $S4 is I, $S5 is j, added, and then it is stored back to $S3, which is given by h. Okay, and then we jump to label 2, and this is an unconditional jumping. So you see, within this piece of code we have both conditional and unconditional statements, control flow execution. Okay, the conditional control flow execution is given by BQ, and the unconditional control flow execution is given by jump, which is j to label 2. Now label 2 could be any part of the code, or it could be the main program itself. Okay, so pretty clear, right? So in this example, as you could see, it appears to be a very simple example in C code, but when we do it using MIPS code, a lot of things have to be taken care of precisely. Okay, and also if you want to do it, if you want to work it out manually, you'll have to assume a certain association of the compiler to its register number for a given variable. Then only you can start doing it. Okay, so let's start with the next example. Now this example is pretty interesting, because in this what we are trying to do is that we are trying to load a 32-bit constant value onto a register. Usually if you see the I-type format, it will have a 16-bit value but not a 32-bit value, right? But here what we are trying to do, what if we try to load a 32-bit constant into a register? So there is a way to do this. So one of the ways to do that is if we could use something called LUI and ORI. So LUI stands for load upper immediate. Okay, load upper immediate. That means we are loading the upper 16-bit value, okay, of the 32-bit constant into a certain register. So here let's say the upper 16-bit value is given by this number 10 10 10 10 10 so on till 10. That is loaded onto register $T0. Fine. Once it is loaded onto the register $T0, which is the upper 16-bit value of the 32-bit number, then what we'll do, we'll try to OR this register value with the lower 16-bit value. Okay, so therefore we have ORI $T0 comma $T0 comma the lower 16-bit value. So what happens after execution of the first statement LUI, the content of the 32-bit register would look something like this. That you see the upper 16-bit number is the number which was specified in LUI instruction, and the lower 16-bit were all zeros. Okay, I'm talking of the first line of binary numbers. And in the second example, in the second line after the execution of the second instruction, you see the lower 16-bit number has also now gotten into the register, which is given by 10 10 10 till 11. So that lower 16-bit comes here, and the upper 16-bit comes to the upper 16-bit of the 32-bit register due to LUI, and the lower 16-bit of the 32-bit constant comes due to ORI. Collectively, after execution of both, the content of the register now loads the 32-bit value, which is given by the last binary number shown in red arrow. Right? So now you see it's possible. It's possible to load a 32-bit constant into a register. It's not only possible to load a 16-bit number, but it is also possible to load a 32-bit constant into a register. Okay, so that is also doable. Okay, now let's move a little forward from the examples, because we've done quite a few examples now, and we've seen different varieties of examples to demonstrate how MIPS actually works, or how you can convert a high-level code into specifically machine language and its assembly language code. So now we'll little deviate from that topic and move to another type of topic, okay, which also has to do with MIPS, but it has to do now with more about determining the target address. So let's say I want to calculate the jump target address. How do I do that? So let's say the jump instruction, if you remember, if you recall the J-type instruction format, it had two fields. First was the opcode field, and second was the pseudo direct jump address, if you recall, right? So 26-bit of that and 6-bit of opcode. So that makes it up as 32-bit. Let me take an example. let's say the jump instruction format or J-type format has the following content. You have 000010, which is a standard fixed opcode of J-type instructions for jump, and the remaining 26 bit is given by the number that you see inside the purple box. So that is the 26 bit target field from the jump instruction. We call that as target field. Okay. Now from this content, if I have to evaluate and calculate the 32 bit jump address, target address, because we have the target field, from there now we wanted to compute the target address of the jump instruction. What we can do? The rule of thumb is that the first point in order to compute the address would be to get the data from the current PC plus 4. Okay, PC is called program counter. This is probably a new term you're hearing. PC stands for program counter. It's a register. It's nothing but a register that holds the location of the current address. Okay, current memory address is location. It holds the address of the current memory location. Okay, for the current instruction where you are right now. So if you want to compute this, the first upper 4 bit, which is 31 down to 28, has to be extracted from PC plus 4. Okay, PC plus 4. The next 26 bit of that 32 bit address has to be taken from the immediate field of the jump address. Okay, and so that gives you 30 bits, and the remaining lower order 2 bits have to be 0. In other words, the 26 bit target field is actually left shifted by 2 positions, right? Automatically by left shifting by 2 positions, the lower order 2 bits becomes 0 0. Or in other words, you can assume that the value in the 26 bit target field is multiplied by 4. When you do the multiplication by 4 or left shifting by 2, it is the same thing, right? So that content now makes it up as 28 bits. Okay, the lower order 0 0 and the 26 bits gives you 28 bits. Or if you just, so one way is just to append 0 0 and the 26 bit target field, other way is to multiply that 26 bit target field with 4, or the other way is to left shift that 26 bit target field by 2 bits, and you get a 28 bit number. This has to be now appended with the upper 4 bit of the current PC plus 4. This PC plus 4 is called updated PC, right? As I said, if the location has to be a multiples of 4. The locations in memory has to be multiples of 4 because we are storing 4 bytes in every location, right? So therefore updated PC is given by PC plus 4. So that upper 4 bit of PC plus 4 plus 26 bit of the immediate field of the jump instruction plus lower order 2 bits, which is 0 0, gives you 32 bit complete jump address. Okay, in the next slide I'll also show what is the generic formula. Okay, so let's see. So how to calculate the target address of branch first, and then we'll move to how to calculate the target address of jump. So in case of I-type formats for branching, the immediate or target label is equals to target address minus PC plus 4, whole thing divided by 4. That is 4 multiplied by immediate field plus PC plus 4 gives you the target address. So that's the generic formula. So example, if you have something like $S1, $S2, 25, where 25 is the target label and not the target address, right? So the target address can be computed as follows: 4 times 25 plus PC plus 4. Here 25 is the value in the immediate field, plus PC plus 4 gives you the total value of the target address for branching. And now how to calculate the target address for jump? For J-type formats for jump, the formula is slightly modified. The immediate or target label is equals to target address by 4 that is target address is equals to 4 times immediate. So as you could see that this 4 times immediate, which I am calling as the target address, is not a complete 32-bit address yet, right? This only forms the lower 28 bits of the address. To form the 32-bit address, the updated PC must be concatenated with the upper 4 bits, which I just spoke in the last slide, if you recall, right? So that is exactly what I'm doing. I'm trying to multiply that target field of the jump with 4 and then add that with the upper, add means concatenation based adding, appending the upper 4 bits of the PC plus 4. So in case if you have something like j equals to 2500, where 2500 is the target label and not the target address. So target address is calculated as 4 into 2500, which gives you 10,000. Second example is you have something like JAL 2500, where 2500 is the target label. So in this case, the label will go to 10,000, which is the target address, but after it finishes execution in that particular location, it has to come back to the return address register, which is specified by PC plus 4. That's an implied part in this instruction. That's why it is called jump and link, because we are jumping to a specific target address which is 10,000, or we are jumping to a particular label which is 2500, finishing the task there and coming back onto a location specified by PC plus 4. That location is specified inside a register which is $RA. Okay, so what we could see here basically is that that the way to calculate the target address for jump and branch is slightly different. The rest of it remains same. Okay, now let's do another example. This example actually uses jump, branch and everything. That's why I had kept this example right at the end. Let's say you have an instruction while save I equals to k, I equals to I plus 1. So we are assuming register $S6 stores the base address of save. Okay, that's the base address of the array save. I is associated with $S3, k is associated with $S5. So in this case, the very first thing that we'll do is again same. We'll have to multiply the value of the index I with 4, because we want to compute the offset. I is the index and we want to actually get the offset value, so we'll multiply that with 4. So in order to do this 4 into I, what we'll do, we'll shift left by using the instruction SLL, shift left logical. So $S3 is shifted left by 2 bits, that is multiplying by 4, and stored into $T1. Once it is stored into $T1, we will then add the value of the base address which is stored in register S6. Okay, once it is added, we will again store it back into the same register which is $T1, and then from $T1 with an offset of 0, we will load the word into a specific register which is $T0. Therefore we have a third instruction LW, which is $T0, 0, $T1. Okay, it's a temporary register, and then we'll check the condition BNE $T0, $S5. If they are not equal, then we'll branch to exit. That means if the content stored there in T0 and S5 they don't match, we'll exit. So that is actually checking that while condition that you see on the top. So you can imagine, just to do that while condition, we had to do so many things prior to that in case of MIPS 32-bit, which we could have simply written a line of code for C. And if they are equal, we'll not exit, and then we'll move to the next statement, which is ADDI, which is actually talking about I equals to I plus 1. ADDI $S3, $S3, 1. That means we are doing I plus plus, incrementing I by 1. And then we'll go to the next statement, which is J, that means jump to L. Okay, L means again go to L, going back to the same place given by the label L, right? So you see, we in this piece of code we've used jumping, we've used branching, we've used load Arithmetic, almost pretty much simple one line code of everything. Okay, so now let me move to something called pseudo MIPS instruction. What is pseudo MIPS instruction? It's basically those instructions which have a way for the designer to be written, but actually internally MIPS converts it into certain set of its own predefined instructions. Okay, so these are instructions that is just used to facilitate the designer, but not useful for understanding. So whenever we write this, eventually it gets converted into an internal representation. So let's start with the first one, BLT, branch on less than $T1, $T2, L. This means that if the content of $T1 is less than the content of $T2, then we'll go to L. So this is actually written as SLT, $80, $T1, $T2. That means $80 will be set to 1 if the content of $T1 is less than the content of $T2. Okay, that will be set to 1. And if this is not equal in the next statement, then we'll jump to L. So this is exactly implementing or mimicking the instruction BLT, right? Branch on less than. Only if it is less, then we'll jump. Okay, that means the content of T1 has to be less than T2, then we'll do a jump or branch rather to a label L, else we'll not do that. Similarly, BLE is $T1, $T2, L. This can be written as SLT $80, $T2, $T1. BQ $80, $0, L. This again mimics the same instruction. If you cross verify yourself, you will see this exactly mimics BLE instruction. Similarly, we have BGT and BGE, branch on greater than equal to, branch on greater than. Okay, so these are some of the pseudo MIPS instructions that we see. Let's move to some other types of pseudo MIPS instruction. There are a few more. Okay, let's say one of them is called MOV $RT, $RS. So this is actually written as ADDI $RT, $RS, 0. So we are adding 0 with the content of $RS and storing it into $RT. This is same as moving $RS to $RT. Then we have LI $RS, small. Small is a 16-bit number. So that 16-bit number is added with $0 and the content of that is stored to $RS. So this is same as loading directly a 16-bit number into register $RS. LI $RS, big. So big is a 32-bit number. So here what we can do is we'll again use the same two combination of instructions, LUI and ORI. In LUI what we can do, we'll have an upper 16-bit of the big 32-bit number and we'll put it into $RS, and then we'll OR the lower 16-bit with the content of $RS and store it back again to $RS. So that actually loads or load immediate for a big 32-bit number into $RS. Let's go to the next example, which is LA $RS, big, which is load address a 32-bit number into RS. Again we can do the same process. We'll use an LUI followed by ORI. And last is LW $RT, big $RS. Here the upper 16-bit of the 32-bit number is stored in $T0 using LUI. Then it is ORed with the lower 16-bit number and stored it back into the same register, which is $T0. Once that is done, then now we have actually loaded the 32-bit number into T0. It is then added with the base address, which is $RS, right, the third statement, and the result is again stored into $T0. So therefore we have add $T0, $RS, $T0. The third statement actually computes the effective address. Once you have the effective address, then again with an offset of 0, we can load the word directly into $RT. So that one piece of line that you have will have internal 4 different MIPS instructions for a MIPS assembler. Okay, in case it's a 32-bit number. Okay, so in this lecture, you've learned a lot of things. You've learned so many different complex examples of MIPS. You've learned about pseudo instructions. You've learned about how to load a 32-bit constant using LUI ORI. You've also learned about how we can break pseudo instructions into multiple internal MIPS instructions, which is understandable by MIPS processor. And you also understood about how to compute the target address for jump, target address for branching. You also understood about how the basically the way to convert a target label to a target address is possible for jumping and branching both. So we actually learned a lot of things in this particular session, and in the next lecture I'll move on to a new topic which is on multiplier hardware, and I'll also talk a little bit about MIPS ALU together. Okay, and if you would like to read more about this, I recommend to refer to the book that you see at the bottom of the screen. Please refer to this book for more advanced level knowledge and to practice yourself to get more insight and depth idea about this topic. Okay, thank you so much.